The last material that we were covering recently was molecular geometry, and we were figuring out the last of VSEPR structures. Right, and so we were talking about where this comes from is we need to determine the ultimate geometry and bond angles of a molecule by considering the numbers and pairs of electrons that we have to deal with. So the first step, and why this comes nicely after Chapter 8, draw the Lewis structure. The first step for Chapter 9, draw the Lewis structure, and then after we determine the Lewis structure, figure out how many electron domains we have, and then after that, determine, okay, what would be the approximate geometry of that molecule by deciding we want those electron domains to be as far apart as possible in space. And so if we have two domains, that was our linear geometry, 3 domains, trigonal planar, and 120-degree bond angles. 4 domains is tetrahedral with 109.5. 5 domains, trigonal bipyramidal, and this was the first case that it was unique because now we have 2 different bond angles. We have 90-degree bond angles and 120-degree bond angles. 120 around the equator and 90 from the axis to the equator. And then the last one we talked about was octahedral, where everything returns to 90-degree bond angles. And so after determining the number of electron domains, we then use table 9.2 to determine the electron domain geometry and the molecular geometry. And so in some of those cases where the electron domain geometry, where all of those electron domains were bonding domains, right, and no non-bonding domains, in those cases both the electron domain geometry and the molecular geometry were identical. However, in some cases we saw that the electron domain geometry and the molecular geometry were different. So for example, when we had 4 electron domains and we were tetrahedral, right, if 3 of those domains were bonding and 1 was non-bonding, we'd be trigonal pyramidal, and that was the case that we saw with something like ammonia. Or when we talked about water, for example, with water, right, we have 2 bonding domains and 2 non-bonding domains. So that was the bent molecular geometry, even though both of those have the same electron domain geometry of tetrahedral. The same continue with trigonal bipyramidal and octahedral, just depending on how many bonding and non-bonding domains each of those structures contained. So the last one that we just got to, or we're just getting to in class, was the octahedral electron domain geometry. And so when we have 6 electron domains, right, we're going to be octahedral geometry. When all of those electron domains are bonding domains, then we will also be octahedral for our molecular geometry as well. And when we have some bonding interactions and non-bonding interactions, that'll just depend on how many of those we have. So the ones we didn't get to in class, the iodine pentafluoride and the xenon tetrafluoride, we'll work through and show what those look like and how to determine what are their ultimate molecular geometry based on their electron domain geometry. So the iodine pentafluoride, right, iodine has, so our first step, right, what is our Lewis structure? Iodine has 7 valence electrons. I've got 5 fluorines that each have 7 valence electrons for 35 electrons. So I've got 42 electrons I have to assign. The xenon is a noble gas, so that would have 8 valence electrons, 4 fluorines for a total of 28 valence electrons there. So 36 total electrons I have to assign in the xenon tetrafluoride. So we'll do the iodine pentafluoride first, right? We put the least electronegative atom in the center, so there's iodine, and I'm going to flank it with all 5 of the fluorines. So fluorine, 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 and fluorine. Well, I have 42 electrons. There are 2 electrons in each of those bonds, so I just assigned 10 electrons. I've got 32 electrons left, and now I'm going to assign those lone pair electrons, right? The second step is I want to fill the octet of the surrounding fluorines. So to do that, I'm going to assign 6 more electrons for each of the fluorines, and 6 times 5, that'll assign 30 of the remaining 32 valence electrons I have to assign. So I had 32 electrons left. I just assigned 30 of those electrons. I've got 2 electrons left. Where will those electrons go? I filled the octet for all 5 of the fluorines, and I cannot break the octet rule for fluorine. Those remaining electrons would have to go on iodine. So if I look, I have 6 electron domains. Right, here's an electron domain, 1, 2, 3, 4, 5, and 6. So 6 electron domains. 5 are bonding domains. And 1 is non-bonding. So because we have 6, right, we'd be octahedral for our electron domain geometry. And then for my molecular geometry, right, we would be square pyramidal. The xenon tetrafluoride, again, we put the least electronegative atom in the center, which would be xenon. I'm going to surround it by my 4 fluorines. Okay, there's 4 bonds, that's 8 electrons, so I assign 8 electrons. I had 36. That's 28 electrons left. I'm going to fill the octet of fluorine. So 6 more electrons for each of the fluorines. And I have 4 fluorines, so 6 times 4, 24 more electrons I'm assigning right now. So 28 minus 24. I've got 4 electrons left. Where will those electrons go? 1, 2, 3, 4 as lone pair electrons on xenon. Again, that's fine. Xenon breaks the octet rule, but xenon can break the octet rule because it has access to d orbitals. Again, just like with the iodine pentafluoride, xenon tetrafluoride has 6 electron domains. Of those 6 domains, right, 2 are non-bonding, and then the rest are all bonding domains, 3, 4, 5, and 6. So again, we would be electron domain geometry of octahedral, but ultimately our molecular shape, which just depends on our bonding interactions, our bonding domains, we would be square planar. And then the last bit, and this came up in class a little bit when, okay, what happens if I have more than one center of my molecule, right? Everything we've looked up to this point, it was easy to determine the geometry because we had one atom in the center and then atoms surrounding it. So it was easy just to say, okay, we know the geometry based on that one atom. But here's a case. I've got acetic acid. What would be the geometry of acetic acid? And now we can actually look at it on a couple different places. We can look at this first carbon, the second carbon, or the oxygen, and to determine the geometry at each position. Because acetic acid is not planar and a flat molecule is written. I certainly do not have 90-degree bond angles as these are drawn here. So to determine the overall geometry, we would do the same steps we did before. So I would look at the first carbon, carbon 1. For carbon 1, I would count how many electron domains I have, right? I've got 4 electron domains around carbon 1. I have 1 domain, 2 domains, 3 domains, 4 domains around carbon 1. So based on those 4 electron domains, right, I would say 4 electron domains. If I have 4 electron domains, I would be tetrahedral. 4 electron domains, and they are all bonding domains. So my electron domain geometry and my molecular geometry is tetrahedral. My bond angles should approximately be 109.5 degrees. My second carbon, I have 3 electron domains around my second carbon, right? Here's a domain, and here's a domain. If I have 3 electron domains, I would be trigonal planar. All 3 of those domains are bonding domains, so trigonal planar with respect to both my electron domain geometry and my molecular geometry. Because I'm trigonal planar, right, my bond angles would be approximately 120 degrees, so it wouldn't be the 180 as written there, or as it's drawn, right? It'd be closer to 120 degrees there. And now for my oxygen, again, I'm going to count how many electron domains I have. For oxygen, I would have 1, 2, 3, 4 electron domains for oxygen with respect to oxygen. 4 electron domains, again, that would put me in tetrahedral electron domain geometry. And then my molecular geometry would be bent. So approximately bond angles of 109.5. It will be slightly less than that because of the lone pair electrons on oxygen. So that's now, we can look at a larger molecule and determine atom by atom what should the geometry be. So the carbon 1, we're tetrahedral. Carbon 2 would be trigonal planar, and then the oxygen, again, I would be a tetrahedral electron domain geometry. My molecular geometry would ultimately be bent. So certainly not a flat molecule as written.